Hello, my name is Matthew Young, and I'll be going over kernel development number 7. So to begin, we start by transitioning the kernel segment and data descriptors into C language. So in this section, we implement the kernel segment and the data descriptors in C. This is so we can prepare for future developments involving user and data selectors for user processes. We start by modifying the config.h file, and we set I'll open it up real quick so we can take a look. Yeah, and then we set a definition um, right here, total GDT segments. This definition basically states the total number of segments and selectors that will be used. Um, at the start of the lab, it starts with 3, but eventually it gets up to 6, and I'll explain that later. After that, I create the GDT ASM file, and what this is going to do is this is going to interface with the processor at the assembly level to load the global descriptor table, or GDT. This file is going to contain the assembly function GDT load, which is required to set the new GDT. After that, we create the header file for GDT operations, which is gdt.h. Basically, this defines the structure and prototypes for the GDT operations, and we actually implement those inside of gdt.c, and this holds all the implementation of the GDT related functionality, but in C. So then following that, we begin by integrating GDT initialization into the kernel, and I don't have it open. Let me open it real quick. We modify kernel.c. Basically, we added some new headers that are required for the GDT related operations. And then we also define the GDT structures as well here at the bottom, as well as TSS, but I'll get into that later. So it's this chunk of code here. And then we also initialize the GDT inside kernel main. Through this chunk of code over here. And I also updated the make file as well, but I won't really go through that since it's the same process as in past labs. In the next section, we begin implementing task state segment, or TSS, that I mentioned earlier. The TSS is used for task switching and for setting up a stack for the processor to use when it transitions from user mode to kernel mode. This is helpful for handling system calls and hardware interrupts in a multitasking environment. First, we start by making tss.h. This is the header file. Um, this is used to contain the structure and function definitions, which I do have open over here. Another part of this as well, we need to implement the TSS load function in assembly, which I have over here in tss.asm. To actually load the TSS, we need to provide the implementation for the TSS load function, and this is done via this assembly code over here. And this helps set up the foundation for task switching and handling system level events in the multitasking environment. We also modify the header files in kernel.c as well. And then after that, we need to declare the TSS structure in kernel.c, which is that block of code I showed earlier that also contained the declaration for the GDT definitions as well. So it is this block here. And then we also, same as GDT, we initialize the TSS within kernel main. And that is done over here in this chunk of code. And this helps like set up future implementations for privilege level changes, system calls, and multitasking. And as I said earlier, the config.h file got changed as well, and the number of segments got increased from 3 to 6 to reflect the changes, the addition of the TSS. And then after that, as the next step in the lab is implementing task foundations. So now that the GDT and TSS are set up, I can now also begin laying the foundations for the task management. The task management basically has different aspects. It loads the user programs into memory, sets up their stacks, and initializes the CPU states. To begin with that, I update the config.h file to include new definitions that are going to be used in the program and stack setup. And then I also have to update the paging functionality as well to support operations that will be essential for task management. For example, one of the essential ones here is going to be an operation that frees up 4 gigabytes of a 4 gigabyte chunk of memory. And this is done through modifications in the paging.c file. Because we make modifications to the paging.c and create a new function, we also declare that function's prototype in paging.h, so there's a slight modification there as well. And then we move on to the task structure. So the core of the task management system is going to be the task structure. And we start by making task.h for that, which I have over here. And then also, these help define the prototypes of the functions, and then we actually implement those functions in here in task.c. And these core functionalities that we define in task.c are these include task initialization, task creation, task switching, and all these functionalities are used for task management. And of course, there's updates to the make file as well to compile all of this. Following that, in the next section of the lab is implementing processes. So in this section, we prepare for the implementation of processes within our operating system. Basically, I establish some constants in the config.h file. These constants include definitions for the maximum number of memory allocations the user program can make. Right now, we're setting this to 1024. We also define the max processes. Currently, we're setting this to 12. And then another function we need to add, we need to add a function to map the range of physical memory and virtual memory. So this is used to enhance our paging capabilities. We introduce a new function called paging map2, and this allows us to map a range of physical addresses to the corresponding range of virtual addresses, and this is done in paging.c as well. I'm going to go ahead and open it up since we've made quite a few changes to paging.c. Another aspect of this section is that we extend error codes in status.h. So we add one new error code in status, and I don't know if I have it up right now. I can go ahead and open it. Yeah, so the one we add is EIS TKN with the value 8. And what this does is this error code is for situations where a task is already taken or is in an unavailable state. And then we create a new header file after this, process.h, and this is going to help define our process structure. So I have that open over here. And the process structure provides a more comprehensive way of managing and running programs in the system. Since we've already created the structure, we can begin defining the process. We can begin implementing those functions in process.c. So I have that open as well. Um, so this implementation of these functions basically helps lay the foundations for more advanced task and process management system, which allows us to run user-level applications with more control over the execution and the resource usage. And then we move on to the next section, which is part 2 of implementing the processes. So we make additional changes to paging.h. This includes creating a paging line address function. And this basically helps align addresses to the nearest page boundary, and this is essential for memory management tasks like allocating and mapping memory pages. And then we implement those in paging.c, or implement that one function in paging.c. After that, we update the task.h and add prototypes to handle more processes. So we add a process variable, basically, to task.h, which will point to the process that owns the task. And then we also have to implement this in task.c as well. And then following that, we also make a strn copy function in the string.c file. It's a small function basically responsible for copying a string. And this is going to be responsible for copying a string from the source pointer into the destination pointer until a null terminator is found. And of course we have to update string.h because we made this new function. So after that, the next step is to actually load a process from a file. To do this, we implement a function called process load, which takes the file name of the process to be loaded, as well as the pointer to store the loaded process. This is done in process.c. And the function is called process_load. And then following that, we move on to the next section, which is enabling user space execution. And in this section, we extend our kernel to support task execution in the user space. The first part of this is to create assembly routines for the user space transition. And we do that via task.asm, which I need to open. I do not have open yet. Right, so this code is basically responsible for updating the CPU segment registers to use the user space selectors defined in GDT. Next we implemented a function to restore general purpose registers inside of task.asm as well. And we also made a function that's responsible for pushing us from the kernel land to the user land, and this function is task return. We also update the task.h file to include C prototypes for the assembly functions I just mentioned, which I don't have open yet. Let me. Oh no, here it is. Task.h. And then after defining the prototypes, we implement them inside task.c as well. This is the task switch and task run functions. And we also have a function we make called task run first ever task. Basically what this does, this function is the go-to function for starting the very first activity or task that the user wants to run. We update the make files as well, and also the header file to reflect the changes that we made, the new functions. And then we get to the final section of this lab, which is creating the first user program. It's a simple program that is basically what it does is it jumps indefinitely to the same place in memory. We don't actually run the program though in this lab. It ends here at this chapter, but it's just basically writing and compiling it. So first step of that is to create a directory called programs, which I'll show now. And inside that folder is another folder called blank, which has most of the files we use for this section of the lab. And this directory is where our first user program for our operating system will reside. And we start by making a new file, blank.ism, inside of it. And I'll open that up. And what this assembly code does is it just jumps to itself forever. Basically, it doesn't really depend on any resources at all, so it's a good testing starter program to make. To compile it though, we need the linker script and the make file as well. So here's the linker, and here's the make file that's associated with it. So the linker script basically tells the linker where our program is going to be loaded, and the make file is going to help actually compile and create. And then that is pretty much it for the lab. It's just basically like compiling at this point. So I go ahead and demonstrate that this all works, and that is able to compile with the build.sh. Oh, I'm in the wrong directory, I think. Yeah, I need to be in the root directory. So let me do this. Oh, and I forgot to, let me real quick change my terminal name. Okay, and then I can go ahead and compile all this. And as you can see, the makefile compiled correctly. Everything seems to be working without any errors. And that concludes the lab. Thank you for watching.